Okay, so time has started. Let's get going. So remember, organic chemistry, very much chemistry of practice. You really want to be hands-on. Work the problems, practice it, okay? Because what you're trying to do is you're trying to, kind of like a sport or video game or something, you're trying to forge new neural pathways, okay? And that means you really just got to do it, right? Yeah. Okay. And what you're going to find is as you start the practices, they're going to be very hard. Okay, you're trying to form new neural pathways, right? So that's going to come with, just like sport, soreness, right? And effort, and it's going to be difficult, okay? But what's going to happen is eventually those pathways are going to start clicking, and once they start clicking, you're going to go, oh, this is actually really easy, okay? Because it's a class of patterns and a way of thinking, not of brute force memorizing hundreds of items. Okay? Fantastic. Now, to do those and form those pathways, you really, really want to get going on the homeworks and working on them, okay? So if you're having difficulties getting the book done, do the free for now. We'll figure out the book. If you can, you might want to just get the refund and then buy it directly through Norton. As far as I understand, there's not any real significant difference in price. But yeah, so hopefully we can get all that worked out. But as for now, make sure you do the trial and get started with that, okay? Okay, so we're going to work on chapter 1, finish that up today. We'll move on to the next chapter, which is the inter chapter. Seems like it'd be easier to call it chapter 2, but actually it's a great book, and apparently that's what needed to get done. And that is not actually connecting. Why is that not actually connecting? Because that is off. And not turning on when I tell it to turn on. Okay. Yeah, I definitely need to change the batteries out or something. Or get a better angle, I guess. Alright. So, I actually did get a new computer, by the way. So my computer went die on me. Part of the way through the lecture. We'll see if that works. Alright. There we go. So we ended talking on resonance structures last time. And so here you see some resonance structures presented in such a way that they're presented on an energy diagram, okay? So if you were to localize these electrons on one oxygen, what you would see is that they would be much higher energy, okay? Kind of like if you were to take the desk and try to pick it up and move it by yourself, right? It'd be swinging around more. It'd be less stable, okay? If you share that charge among two oxygens instead, they can then support that charge in a more stable configuration, okay? Kind of like if you took two people and moved the desk, right? Then the other end isn't swinging around, is it? Okay? Much more stable. And can you start seeing how you can use what you know and understand of these things to extrapolate out? And so you don't have to memorize a bunch of material because you can very rapidly extrapolate out. All of organic chemistry is, in essence, stability. Okay? What's the minimum energy? What's the most stable? Right? So, these are some different other equivalent resonance structures. We have species that have equivalent resonance structures. These tend to be highly stabilizing. As the number of resonance structure increases, typically you're going to get more and more stable because it means you're sharing charge, you're sharing bonds with more and more atoms. And so it can be more and more stable, right? Or lower energy. This is an example. You may have seen this before. Anybody ever seen benzene ring? Yeah? Okay. So this is actually a benzene ring fully shown, okay? So you can arrange the bonds like so, right? And these individual structures, their proper name is a Kekel structure, okay? Not really super important. I'll be surprised if you ever use it again. I'm pretty sure you could go up to like 10 PhDs in chemistry and go, show me a Kekel structure, and they go, what? I'll be honest, if you caught me at the right time, I might go, huh? If I'm just not thinking of organic chemistry, right? Just call them individual resonance structures if you want people to actually know what you're talking about. Okay? Not the proper name, but whatever. This would be what it looked like as a sum of those structures, right? So each of those carbons has like a 1.5 bond-ish. Okay? Now, when we talk about bonds, do remember that these bonds are going to be flowing. Okay? Electron density is going to be shared among these things. And so it's not going to be perfectly 1.5 on every part of this. All right? It's going to be flowing. Now, you may have seen a structure where they have the ring and they have a circle in the middle. That represents the same thing. Okay? That's actually representing this structure over here. Okay. All right, so this is non-equivalent resonance structures right here. You will notice that these are not actually equivalent to each other. See that? They would not have the same energy, would they? No. This one is much higher energy because of that positive on that oxygen, isn't it? And yet, it does exist. This is something that needs to be represented. Okay? And what this is this happens all the time. Anybody remember with water how it's like auto-ionizing? You have water acting as an acid and base at the same time? Like the high energy states, they don't completely not exist. If they're low enough energy to jump up in there, they exist. And they're happening all the time. Okay? The higher energy you get, the harder it is to actually jump up, right? For example, is there anybody on the third floor of this building? Us. We're on the third floor of this building. Is that a low energy state? No, we're on a higher energy state, aren't we? Okay? Anybody on the roof right now? Probably not, right? Is there the possibility of somebody being up there? Yeah. But it's a very high energy state, very unstable state, right? And so it's going to collapse down very easily, and so it's not happening a lot. Okay? If we were to not have these classrooms filled with classes, they'd probably preferentially populate these closest to the offices, right? Which would be the lowest energy states. Okay? Does that kind of make sense? Fantastic. So this is a higher energy state over here, this one. But it's one that's low enough energy that we could pop up into it a fair amount of time. Okay? And what this means is this state right here, what do you think is going to happen with the hydrogen there?
Break off.
Yeah, it's going to break off, right? And this is one of the reasons, this is carboxylic acid, right? Specifically, this would be formic acid, like ants spray on you. Yeah, that's that stinging sense that if you get bit by an ant, the small ones, not the big jaws. Or ladybugs. Anybody gotten bit by a ladybug? Asian beetle? No? That smell you smell when you crush them, that's formic acid. They're tanning you. It tans your flesh. Like a leather jacket. Okay? Anyways, this is why that's acidic right there. Right? That's part of the reason. And the other part of the reason is when this is lost, it gets to share that negative charge among the two oxygens, and that's very stable, isn't it? Okay? And so that actually is that entire acidity for carboxylic acid, formic acid that you guys were looking at before in the previous classes, like vinegar. That's it, right there. All right, so any two resonance structures are going to differ only where the electrons are located. The atoms must remain frozen in place or else you're going to get lost and you won't be able to figure out what's going on. Okay? You got to keep the atoms in the same place or else you won't know what's going on. So we represent the movement of electrons by using curved arrows. We curve the arrows to show the movement of a pair of valence electrons. And that's these curved arrows right here, right? Okay? If you have two tines, everybody know what a tine is? No? Okay. An arrow 1 tine, 2 tines. Okay? That's what those are. Okay. So if we represent 2 tines, that means we're moving 2 electrons. If we do one with just 1, that would be 1 electron being moved. We always represent where the electrons are moving because which thing is going to move easier? Electrons or atoms? Yeah, which do you move? The seat or do you move the building? The seat. That's about the same weight difference, by the way, as an electron versus an atom, right? Yeah. So, okay. So right here we actually see electrons moving, and we're representing them moving, and see how we're moving these electrons up onto that oxygen there, and we're moving it from the oxygen into a bond over here. Can everybody see that okay? Okay, is that making sense? Mm-hmm.
So since both of those structures have charges to start with, does that mean they're like roughly the same energy level?
For this one, yeah. They should be the same energy level. And so they should be degenerate in their energy. Yeah. They wouldn't be like that other one where we moved it onto a double bond with a positive on the oxygen. That would be much higher energy. Yeah. Yeah. And so these two, because they're equivalent on both sides, this would end up being same energy. Yeah. So anybody have any questions about that so far? Everybody understands that we're following how the electrons are moving, and we're moving them around into bonds, etc. Mm-hmm.
So this is just saying, like, to show a resonance structure, instead of like the dotted line, use those arrows?
Yeah, so the dotted line version would be the sum of the different resonance structures.
Okay.
Yeah. So that's representing kind of more like it would look in the real world. Or another way of saying that is we're just merging all the resonance structures into one thing. Yeah. These are showing the individual, and I'm kind of building you up to reactions. Okay? So reactions, we're going to be moving electrons around as well. Okay? And we'll be using the same terminologies. Okay. A quick little note, by the way. How do I figure out how many bonds I should have on each thing? How can I easily figure out what's a positive, what's a negative? Yeah, you could do formal charge, but that's going to take a bit of time. The easy way to do it is the number of bonds things typically want. Okay? Carbon wants how many bonds? 4. If we have 1, 2, 3 bonds on this far right one, what charge do you think that's going to be? Positive, because it doesn't have extra electrons, right? If we have a pair of electrons that were on it, that would then be negative, wouldn't it? Okay? Because instead of sharing that extra electron, it had an extra electron on it. Does that make sense? It's formal charges, but just done faster. Okay? As a difference from normal states, right? Rather than going through and doing the whole thing. Okay. Eventually, what you'll do is you'll find as you practice these things, you'll start getting that down. And you'll just be able to pop off. Carbon has 4 normally. It's lacking a bond here, no extra electrons, has to be positive. Okay. Oxygen normally wants how many bonds? 2. Yeah, you got it. And so again, normally that's something you're going to absorb as you practice. Okay, so right here we have a polar double bond, and so the other Kekel structure, or the other resonance structure here, is going to involve moving the electrons up from the double bond onto that oxygen, right? Why do I select the oxygen? Why isn't it the carbon?
It's more electronegative.
More electronegative, exactly. Exactly. Same reason I'm not moving electrons onto those hydrogens, right? Okay. Fantastic. This is that same benzene, by the way. Note that resonance structures are typically represented with brackets. They have to have brackets. And that means that they are the sum of in a single structure, right? Okay. Okay. So right here we have, frequently a species will have more than 2 resonance structures, especially if it has delocalized electrons especially if you start seeing these lone pairs and charges like that. Okay? So delocalized electrons, like double bonds, they're near something that's also delocalized, has a very high tendency to have resonance structures. Okay? Okay. And that's what we're seeing here, actually. So this can go into a bond, create a double bond, and then this double bond moves over, right? And we can actually do that, bumping it over each time by 1. Okay? And those are different resonance structures. Okay. So these are the shorthand notations. So when we learn the organic chemistry, it's going to require drawing numerous molecules. Drawing out detailed Lewis structures each time is going to be incredibly tedious and would just multiply this course's time for you to practice problems, do anything in it, by 3 or 4 times, right? Very, very long. So we have to have shorthands, we have to have namings so we can save time, so we can represent fairly long, complex structures in short distances. So right here we see an actual drawn out structure, and this is a Lewis structure. There are more explicit structures that provide more information, but they're even longer, and I'll introduce you to them. Every now and then you might need one. Okay. This right here is shortened, and you see how we've collapsed all the hydrogens in, so we aren't expressing their bonds. Everybody see that okay? Okay. And then this is the name of that compound right there. Okay. All right, so these are the different formal charges on atoms with various bonding scenarios. This is not something that I would recommend you sit there and memorize. It's something that you'll pick up during practice, okay? And you'll just get used to. But again, this is your formal charge of 0, has 4 bonds on the carbon. If you have a lone pair on the carbon and 3 bonds, that would be a -1 charge, right? These things are going to be the stuff you'll see the most. Does anybody have any questions on this? This table is only going to see any use when you're just starting. After doing like 1 or maybe 2, maybe 3 chapters max, you'll never look at this table again, okay? You'll just have practiced enough times, it's automatic. These are condensed formulas. So again, this is the condensed formula right here, and it allows us to include molecules and molecular ions as part of your regular text. Notice you can actually write it out on a text line. Okay? Do note that you need to understand a few little things here. First off, you need those normal bondings, right? Like, what are these hydrogens bonded to? The carbon in front, right? Okay. And what's the carbon bonded to? The next carbon, exactly. You can't have a hydrogen in the middle. Why can't you have a hydrogen in the middle? Yeah, it can't make 2 bonds, right? Only the carbon could make more than 1 bond of those options. Yeah, and so see these parentheses? What do you think that means? So look at the CH3. How many bonds does carbon usually make? 4. And so it already has 3 consumed, right? So it's probably not going to be in the center between things, is it? It's going to have to come off as a branch. Okay? And that's actually this branch down here, right there. That's that carbon right there. Okay? Now, if you look at this carbon here, again, we consumed 1 here, 1 here. One of them's the hydrogen, isn't it? And then one of those bonds goes on to the next carbon, doesn't it? Okay? And you see how you can build this out very rapidly? Just take it one step at a time, simplify, and just go through what are my common bonding patterns. Okay? Don't try to just generate it randomly all at once. In organic chemistry in general, just take it one step at a time. Eventually, your brain's going to start shortening things for you as you practice. But just worry about getting it right for now. Okay? You can go fast later. After you walk, you can run. Okay, so again, we have a structure here. This is ethanoic acid or acetic acid here. Okay. Now note that we can actually have some various different stuff going on. This right here is that structure. And again, how would we generate that? We would just go along and go, what's my common bonding, right? So we draw it as CH3 because CH3 is right there, right? Carbon should have one more bond, so we bond it with a carbon right there. Okay? And then we have these oxygens and a hydrogen. Okay? You may be tempted to try to put the hydrogen on the carbon, right? But quickly what you'd find out is I can't make 2 bonds to those oxygens, can I? Yeah, that's a problem, isn't it? Yeah. And so again, you have a bit of a hint that the hydrogen's going to get attached at the end after the oxygens because it's the next one over, right? There's no parentheses or anything. But you also have a hint because the oxygens take 2 bonds each. Okay? All right, so these are line structures or line edge structures, depending on how you have heard them before. They're labeled slightly differently in every book. So what you're looking at here is they're like condensed formulas, but they're just a faster way of writing the structure out so you can fully express the connectivity and what everything's bonded to. And so this right here was the structure like we were looking at before. It's been slightly condensed, not showing every bond. But this right here is your line edge formula. Okay? You see something missing? What's missing? Hydrogens, yeah. We also don't have any carbons listed, do we? Okay, so every edge is a carbon. Okay? So for example, this right here, that's a carbon, isn't it? This, carbon. What if it was an oxygen? Yeah, we'd have to expressly show it, right? Like this nitrogen right here. Okay? So we would write nitrogen. And we don't have to write the carbons because every edge is a carbon. Got it. How many bonds do carbons have? 4. So this one, right there, has 2 bonds already. How many hydrogens does it have on it? 2. Yeah, it has to have 2 more bonds, doesn't it? Because otherwise we'd have to express some sort of charge. We'd have to express something. Okay? If we express nothing, it just has hydrogens that filled up to 4. Okay. How about this one at the end? So it has 1 bond. It has to have 3 more bonds, right? And those 3 other bonds, those would have to be hydrogens because we don't have anything else listed, do we? Okay. There you go. How about this? It's a double bond, isn't it? How many carbons are on there? 2. There's 2 edges, aren't there? Yeah. So there's a carbon, carbon. Okay. And then there'd be hydrogens coming off here. 2 for each, right? Okay. Okay. Everybody sort of getting the pattern? Okay. Anybody have any questions about this? All right. So this over here has how many carbons? 2. Because each edge is a carbon, right? It's 3 bonds. Yeah, it has 3 bonds, triple bond. How many hydrogens does it have? 1 on each carbon, exactly. Because they have to get to 4, right? There we go. See how fast those are to do? By the way, I'm going to make a little note on these. If you write line edge formulas, which you're going to a lot, this is something we're going to use quite a bit. Okay? Because otherwise writing it out fully just takes too much time. You're going to kill yourself with your time. If you use line edge formulas, always go back and count. 1, 2, 3, 4. Okay? The reason for that is once you start writing these out, it's so fast that you're going to lose count. You can't count as fast as you can write. Okay? And so you always need to go back and double check. And I very much do not recommend writing in something you can't erase. Okay? If you're going to write in something you can't erase, be prepared to really go slow and count it out as you go. Right? Very, very easy. Probably the most common mistake students make actually on homeworks is two things. It is they use a line edge formula, and then instead of having 6 carbons, they have 7. Or they have 5, right? They just don't have the right amount, because it's very easy to mess up. The other major mistake being that they have selected something over on the toolbar, and then they've off-screen right at the edge clicked a bunch of times because they're not like paying attention. And so there's like 20 hydrogens over here slightly off-screen. And I get the answer. I'm like, yeah. That's why it's wrong. So anyways. Specific arrangements of atoms connected by specific types of bonds tend to react in characteristic ways. These structural components are going to be called functional groups, and we're going to modify our structures by these functional groups. We're going to spend a lot of time talking about functional groups because, again, they react the same way. They have similar properties for these structures. Okay? For example, the reason you can smell fruity flavoring and color, that you have fruity sense of smell, is actually ethers. Okay? That's why sometimes when you're like at the gas pump or something, you can start smelling fruity, or you like smell acetone, you go, that smells kind of fruity. That's why. So a molecule's reactivity is going to be governed by the functional groups it possesses. There are several functional groups. They're each going to have their own functional group names. The compounds consisting of only carbon-carbons with carbon-hydrogen single bonds and nothing else are called alkanes. Okay? And you may have noticed on these namings, ane. Guess what that's named for? Alkanes. That's why. All right, so these are some different common functional groups. The double bond is an alkene. Everybody say it with me? Alkene. So alkane, alkene. Okay, last one, triple bond is alkyne. Really stress that. Why? Ein. Come on, say it with me. Alkyne. Now, I'm going to be honest, there's a bit of a disadvantage to being a Southerner when you're communicating scientific terms. This ein versus een does not always come out in Southern dialogue and accents. Okay? So really do actually practice these things, because there is a pretty strong component of what people will perceive of you and your competence and your ability to say the things, right? It's a big advantage if you go to like Harvard or Oxford. You sound smart. And you're not necessarily always smart, but you sound smart, right? And so people think you're smart. This is an arene or an aromatic compound. Almost always called an aromatic compound. Very rarely is it called an arene, but that is the correct terminology. This is an alkyl halide. This right here would be one of the halogens. Okay? And that's typically whenever you see an X there, that usually means halogen. This right here is an alcohol. Yes, alcohol is in like beer or vodka. Okay? Ethanol being the alcohol that would be in beer or vodka. Or rubbing alcohol as well. This is a phenol. Notice it's a combination of arene and an alcohol, right? And so that's phenol. Okay? Yes, every time you've seen phenol in a name, it's meant that. Yeah. Thiol, it's like an alcohol, but instead it has sulfur. So instead of oxygen, it's sulfur. This is an ether right here. That was what I had been talking about before. It's an oxygen in the middle. Easy way to kind of remember that is either side of the oxygen. Ether. This is an acetyl. This comes up a lot with like sugars and stuff, by the way. When you start going into sugars and like biochemistry and such, the naming for them is heavily involved with acetyls. Okay? This is hemiacetyl. This is why the naming for sugars, again, revolves around hemiacetyl acetyl designations. Okay. This is an epoxide, yeah, like the glue. Right? The epoxide glue has epoxides in it. This is an amine. Anybody ever heard of an amine before? Okay. What are proteins made out of? Amino acids. So one side of it is a amine. Or amino being the group when it's attached to stuff, right? This is a nitrile, by the way, like nitrile gloves. They're polymer composed of nitriles. This is a ketone right here. Yeah, every time you hear like keto bodies or keto diet, ketogenesis, ketone. Okay. Aldehyde right here. It's hiding a hydrogen. That's sort of the way you can help yourself remember that, versus a ketone where it's a carbon on both sides of that. Okay. This right here is carboxylic acid. Guess what the other end of a amino acid is? Carboxylic acid. Yep. Ester right here. Notice it's like a carboxylic acid, but instead it has a carbon chain on it. Do you see that R group right there? That means residue. It is a carbon chain that you got too lazy to actually put in. Okay? It means some carbon chain. It could have other stuff on the carbon chain. I don't care. I just wanted to represent a carbon chain of some type. Okay? Okay. This is an amide. This right here is actually the amine. See the amine right there? Combined with something like a aldehyde or a ketone, right? Has a carbonyl group with it. Okay? Anybody ever heard of a amide linkage? No? It's one of the names for the linkages in a protein. Okay? The bond between the carboxylic acid side bonded with the amine side. All right? That's how you make those proteins. So the organic molecules are found exclusively in living organisms. These are going to be called biomolecules. There are actually four major classes of biomolecules. There are the proteins, carbohydrates, nucleic acids, and lipids. And you guys all probably knew all those. Hopefully none of those are surprising to anybody. Okay. So this is actually a typical amino acid. This is the segment of the protein right here. So notice the amino acid, right? See that? This right here is the side chain. I'm doing a general amino acid. I don't care what the side chain is. Okay? The various different amino acids, alanine, etc., have different side chains. All right? This right here is a segment of a protein. Ooh, so notice, by the way, this is the amide linkage right there. See that? And that's how you assemble those proteins, is that right there. Would be the different amino acids assembled. Okay? And so this is a fibrous protein. So this is, for example, like a muscle fiber. Okay? And see how it just goes sort of straightish? That means fibrous. If it went like this, that'd be globular. All right. Anyways, so fibrous protein, symbols in muscle tissue, and we build and build and build from there, right? And we get lots of interesting stuff happening. So some of the features of an amino acid, the amine group is going to be bonded to the alpha carbon, this being the alpha carbon right there. Alpha meaning the first from a functional group. Okay? If you're 2 carbons away from a functional group, what would you be called? Nobody knows their Greek? What's next in Greek?
Beta.
Beta, you got. Okay, they may know what the third one is. Gamma, yeah. And I'm going to be honest, most chemists just get too lazy after that to bother. So, that's actually the reason. After you get the third place from any functional group, its actual effect on that fourth place is almost nothing. So typically you don't really care, but there is, that's delta, and you go on and on. Okay? And you can actually see that if you start looking at like fats are a big one. The beta, delta fats. Okay. Anyways, these amine group, this is the side chain bonded to the alpha group right there. And again, this is carboxylic acid that's bonded to your alpha group right here. Okay. And so these are the naturally occurring amino acids right here. Here we have alanine, leucine. Who here is going into biochemistry? Really? It's not that many people. Wow. Okay. I would have thought a lot more. Wow. I'm pretty shocked. Anyways, if you're going into biochemistry, just start making flip cards and start memorizing that, okay? just go ahead and do it. You'll want the 3-letter code, 1-letter code, because in biochemistry, you're going to have to pop these off so fast that you're really going to need to be able to do the 3-letter and 1-letter codes. Anyways, these are those R group side chains. Does anybody have any questions about that? Okay. Okay. There's some kind of cool stuff, by the way. You see this proline here? It actually wraps around. Did you see that? This is the actual R group here. This is the amino acid. It's wrapping around onto that nitrogen and constraining it. Kind of looks like a P too, doesn't it? It's a proline. Anyways, glycine, alanine, these are some of the simplest ones right there. And I'm not going to go super far into this because you have a whole another class to talk about that. Okay? But, yes indeed. So anyways, these are some of the naturally occurring, again, there's 20 of them. So that wasn't a full list right there. There's more. Histidine right there, by the way. Lysine. You may have heard of those before. Anyways, the naming actually is fully has to do with what we've been talking about. Have you noticed that? Like amine right here. What do you think's at the end of it? Yeah, there you got amine, right? Threonine, 3 different groups on it. Yeah. So anyways, okay, so let's talk a bit about carbohydrates and monosaccharides. So the carbohydrates, these can also be called saccharides. They're going to serve a variety of biological functions. You probably mostly know them in terms of sugar intake, or like starch intakes, probably. Okay? But they're also used for a variety of different purposes in your body. So the carbohydrates are going to be characterized by their chemical composition. Specifically, they'll be characterized by 2 main parts. That is the aldehyde right here or versus a ketone right there. Okay? And so these are known as the keto, aldehyde, or aldoses and ketoses. Okay? Os meaning sugar. Right. This right here is the alcohol. You notice they have alternating alcohols. See that? Okay. Anybody ever heard of a D versus L sugar? Huh? Anybody heard of a D versus L anything? No? Anybody ever bought any like protein supplement or anything? Ooh, you guys are getting ripped off. So, the human body reacts differently depending on the D versus L. We'll go into that a lot more detail in this course. But suffice to say, a racemic mixture, meaning it's both, about equal quantities. If you buy the protein powders, some are specifically one form that's active, and so you get a lot more bang for your buck. If you buy them that they don't say anything about that, they'll probably have equal amounts of both. That's why they're not saying anything about it. And half of it is just junk. You can't digest it. Okay? Or it will have a completely different effect, maybe an adverse effect, depending on what you're taking. Yeah. We'll talk more about that in just a bit, but we need stereochemistry first. Okay. So the size hierarchy of the carbohydrates, they can expand really, really far. You can have monosaccharides, mono meaning one, exactly. So one sugar. And that's a monosaccharide right there, right? We can have disaccharides. Disaccharides meaning two. Trisaccharides, though we typically never talk about trisaccharides. Three. And after trisaccharides, polysaccharides. Yeah, we just give up. In fact, even trisaccharides typically are not ever used or brought up. Polysaccharides just meaning many, right? Like polyglot. Okay. And so what does this like bond with a squiggly mean? Yeah, we just are saying it goes on, right? How much doesn't matter, right? We don't care. And so whenever you see this where it's like a bond with a squiggly, it means it extends on. And we just don't really care how far. Okay? It could extend for 1,000,000, it could extend for 3. Just doesn't matter in this case. So this right here, see how these interchange and have a little equilibrium sign between them? Okay, 99% of the sugar in your blood is actually that form right there. It's the closed form. Okay, closed chain form. This right here is the expanded chain form. Okay, the vast majority of sugar is not like that in your blood. All right, despite the fact that almost every drawing you've seen probably is of this form. And these right here, again, are the fibrils, and that's actually those right there. And then you put them together, they make the bundles. You put them together, they make the cellulose. You put them together, they make the plant, right? Okay. And technically, you're wearing forms of cellulose, and you have cellulose all around you, right? I don't know how much of the stuff in here is actually wood versus plastic. Probably most of it's plastic. But some of the newer plastics are actually made of cellulose, which is pretty cool. If you go by my office, I actually have drinking cups made of them. They look like plastic. They feel a bit like wood. So nucleic acids and nucleotides. We have a nucleic acid. It's a large molecule chain that is primarily associated with storage and the transfer of genetic information, of course. And again, this is a nucleotide. See, it has all that structure to it. We have the phosphate. That'll make the phosphate backbone. Anybody know what that is? Yeah, so this one's deoxy because it doesn't have an oxygen right there. And then it's ribose, it's the sugar. And then nucleic acid being this stuff, right? Fantastic. These will assemble into the double helical DNA. And this is actually one of those right there. Okay, and so this backbone here, that's composed of those phosphates with those ribose groups in there. And then these things right here are actually the bases. Okay? This aggregates, wraps together into the chromosomes. 23andMe. Anybody know how many chromosomes you have? Yeah, so 23andMe actually was a hint, right? 23 from each parent gives you 46, you got. Okay. So the features of your nucleotides here, again, has the cyclic sugar here, the phosphate group that bonds to the next cyclic sugar, and this right here is your nitrogenous base here. The phosphate group is an inorganic phosphate group. The sugar is a monosaccharide, specifically ribose. And then the nitrogenous base, that's actually the identifier that gives you the A, T, C, G, U. That's the difference right there. U only being an RNA, which has the oxygen off of that sugar. Down here, there's an OH for RNA. Okay. Anyways. So again, the RNA, this is going to have 4 nitrogenous bases of RNA. Are going to be uracil, guanine, adenine, and cytosine. They're abbreviated U, G, A, and C, respectively. The DNA has 4 nitrogenous bases. They're going to be the GAC, same as before. But now we're going to have thymine, which is T. Okay? And so these are actually all of the bases right there. Everybody see that okay? Fantastic. This is the reason they're called nitrogenous bases, by the way, the nitrogen groups in them. Okay, so now hopefully you got some idea of how in the world this all connects to everything else you're going to be dealing with, right? Because these functional groups, they're going to determine how these things react in your body. They're going to determine how everything reacts around you. And so we've related it to everything that exists around you, right? Okay. Okay. Do you have a burning passion now to understand the organic chemistry around you? Whoa. So much less excitement. Okay. All right, so let's talk a bit about three-dimensional geometry. Whoopsie. I clicked on the wrong one. These did not order like I wanted them to. All right. I'm going to have to reorder those sometime. Okay. Let me stop the video here.